Hello, welcome to the Winston Foodservice and FCSI educational seminar on precision temperature cooking. We're going to cover controlled vapor technology compared to sous vide, combi, and traditional convection cooking. The object of this course is to provide knowledge of precision temperature cooking techniques. We will discuss the science and importance behind dialing in precise temperatures to garner ideal food textures, consistencies, and efficiencies. We will explain the differences in wet bulb versus dry bulb temperature and explain technologies and terminologies. We will also cover the performance and differences between cooking systems, showcasing innovative uses for cooking and holding equipment. Combi ovens use three methods of cooking in a single appliance: convection, steam, and a combination of both convection and steam, hence the name. Convection, the circulation of dry heat, can be used to bake bread or roast meats. The steam function is more delicate and ideal for poaching fish, steaming rice, or cooking vegetables to ideal textures. Used in combination mode, combi ovens produce foods that are moist and flavorful with minimal shrinkage. Some of the benefits of combi ovens include multitasking. A combi oven can stand in for a steam and convection oven. Used at lower temperatures, it can also serve as a proofer, holding cabinet, or a slow cooker. While it can carry a hefty price tag, it may be more cost efficient than purchasing multiple pieces of equipment. Combis allow the user to steam, bake, roast, and do a combination. The combi oven is a very powerful piece of equipment. As such, they can produce cooking speed that is unrivaled by any other method. Programmable menus let you hard load or manually input recipes in cook modes. This turns even complex recipes with intricate steam and convection settings into the press of a few buttons. By using both steam and convection in your recipe, you can preserve flavors and nutrients, which results in a higher quality finished product. Moisture from steam helps to prevent meats from drying out and shrinking. Some of the drawbacks of combi ovens include cost. Combi ovens are some of the most expensive pieces of kitchen equipment. Upfront costs are considerably higher than any other equipment. Infrastructure costs for electricity, vent hood requirements result in ongoing higher expenses. Combi also require the use of daily cleaning tablets or chemicals that can add up to hundreds of dollars a year. Combi ovens require regular maintenance, chemicals, filters, and cleaning. Failure to do so can shorten the equipment's useful life. As noted above, combis require the use of daily cleaning tablets and chemicals. Because they are so complex, combi ovens can be prone to break down. Repairing these ovens can be quite expensive. Because combi ovens are so sophisticated, they can be used to produce quite impressive results. But that complexity can supersede the average commercial kitchen's ability to execute. Essentially, the operator is paying for functionalities that will not be used. Most of these units are very complicated to develop settings for and almost always underutilized by the customer. Sous vide cooking. One of the oldest and most simple cooking methods, sous vide, French for under vacuum, typically involves sealing foods in a food-grade plastic bag and immersing it in temperature-controlled water. Typically, an immersion circulator is added to the water. Food is gently raised to the water temperature, cannot exceed the water's temperature. While sous vide works best for cooking meat and fish due to their lower required cooking temperatures, you can also sous vide to cook a variety of other foods, including eggs, vegetables, fruits, and infused alcohols and oils. Sous vide has several advantages. Thermodynamics dictate the food cannot exceed the temperature of the water, so overcooking is virtually eliminated. Concentration of flavor and juiciness. By sealing foods in a bag, internal moisture and marinades are prevented from evaporating away, making flavors more intense. Because food cannot overcook, sous vide does not require constant attention. Staff labor is free to concentrate on other tasks. The length of time it takes for foods to cook versus sous vide practically eliminates the risk of contamination, as the water essentially pasteurizes your food. While there are many advantages to sous vide, it also comes with some disadvantages running sous vide in your operation. Sous vide is, by nature, a slow and gradual process. It is not the technique to employ if you must cook in a rush. Because sous vide tends to concentrate flavors, some flavors can become too intense. Fresh garlic can become overwhelming. Bay leaves tend to develop a dusty or metallic taste. Alcohol, such as wine, cannot be used because of the lack of evaporation. The degree of accuracy required for proper sous vide cooking can require some costly equipment. Add that to the expensive cooking bags and counter space consumed by circulation cookers, costs can quickly mount. Because sous vide does not allow browning, foods such as proteins may require finishing on a grill or a skillet. Sous vide cooking also requires a HACCP plan that can be costly to create and a challenge to implement consistently in a kitchen. Convection ovens. Convection ovens are an improvement over conventional ovens. Convection ovens have fans to circulate air around food, which delivers very even heat. The increase in air circulation causes food to cook faster than in a conventional non-fan oven. Convection ovens can be utilized at lower temperatures than conventional ovens, which helps to avoid overcooking. Convection ovens distribute heat evenly around food, removing the blanket of cooler air that surrounds food when it's first placed in an oven, allowing the food to cook more gently in less time and lower temperature than in a conventional oven. Air circulation helps minimize hot or cold spots inside the oven, so food cooks very evenly. Compared to conventional ovens, convection ovens cook much faster. Airflow makes convection fans more efficient at heat transfer, so food can be cooked at lower temperatures. For example, a food that typically requires 350 in a conventional oven may only take 300 Fahrenheit in convection. Because the heat is not directly radiant, multiple items may be baked without temperature drop. The oven treats the entire oven load of product as a single item. Lack of hot or cold spots means everything cooks evenly. While there are many benefits to convection ovens, there are also cons. Because convection ovens operate so differently from conventional ovens, recipes must be adjusted, otherwise foods will overcook or burn. Convection ovens have a lot of moving parts, each which can fail. Repairs tend to be expensive. Too much product can hinder performance. While you cook several dishes at once in a convection oven, if you overcrowd the oven or block the fan, efficiency will drop. This can lengthen cook time or damage the product. Controlled vapor technology. Controlled vapor technology, or C-Vap, is a cooking and holding technology that uses a dual heat system of dry, sensible heat and wet, latent heat. Working in tandem, this dual heat system delivers very precise control over food temperature. It comes down to a matter of wet bulb temperature versus dry bulb temperature. A temperature-controlled air heater provides radiant heat and controls the oven temperature. The source of the water vapor is a water body in the food chamber provided with a temperature-controlled heating system called an evaporator. These two heating systems are housed in a closed chamber to precisely control each temperature independently. The units are fitted with a microprocessor to control the water vapor by controlling the evaporator temperature and the air temperature relative to the evaporator. The microprocessor makes it possible for the end user to select final food temperature with assurance as to its precision. Controlled vapor ovens have many advantages. C-Vap ovens are extremely precise. They match the accuracy of sous vide cooking without requiring foods to be immersed or even bagged. Oftentimes, bagless cooking is possible. The accuracy of C-Vap ovens make it possible to get repeatable results. This is critical for operations with staple dishes where customers' expectations for consistency are high. The variability of the dual heat system means that many different cooking methods can be used, including steaming, baking, braising, staging, hot holding, sous vide, confit, and more. The performance of C-Vap ovens approaches that of a combi and high-end convection ovens at a lower cost. Because C-Vap ovens do not require vent hoods, they need a fraction of the utilities and infrastructure that combi ovens require. C-Vap ovens also bolster large capacities, allowing you to cook up to 28 hotel pans or 14 sheet pans simultaneously. This gives substantial capacity as compared to a combi or convection oven. While C-Vap ovens' max temperature is 350 degrees, they cannot match the speeds of a combi oven that can get to 450 degrees Fahrenheit or high-performance convection ovens. C-Vap ovens cook very evenly, but browning can be a bit uneven when attempting to cook loads quickly. As the evaporator and air temperature may be very high during the cooking process, it may not lose heat fast enough if moving directly to a holding setting. So what is wet bulb versus dry bulb? There are two different kinds of basic heat. Sensible heat, meaning that one can sense or feel it, is heat traditionally used to cook food. It is also referred to as dry heat. It can be measured with a thermometer, which uses a dry bulb, hence dry bulb temperature. Latent heat, on the other hand, is measured with a simple thermometer having a wet sensing bulb, hence wet bulb temperature. For a thermometer to be considered a wet bulb thermometer, it is necessary for the sensing bulb of the thermometer to remain wet. Since wetting must be maintained while moisture is being evaporated, the sensing bulb is normally fitted with a woven cotton gauze tube, then wetted. An obvious example of latent heat is steam. All water has a vapor pressure. For example, water at 212 Fahrenheit has a vapor pressure of 14.7 psi, or pounds per square inch. If heat is applied to a body of water to raise its vapor pressure above the vapor pressure of the atmosphere around it, it will evaporate. The heat applied to the evaporate is stored in the vapor. This is latent heat and was due to a change in state, liquid to gas. The vapor is a gas, and it gives up its heat to object onto which it is condensed, change the state of gas to liquid. If we place two wet bodies with different temperatures in an isolated chamber, they will become the same temperature. The one with the higher temperature will have the higher pressure. The difference in pressure will cause a small amount of water to evaporate from the hotter water to cool it and flow to the cooler water, condense onto it, and heat it. This process will continue until they are both the same temperature. The one that was hotter initially will have lost some of its weight. The one that was cooler will have gained the weight lost by the other. So, if we control the temperature of one water body, it will control the second. Another example illustrating the effectiveness of evaporation condensation phenomena to control food temperature is through evaporative cooling. As a range heats a pot of cold water, it warms it at first without evaporation. Evaporation begins only after its vapor pressure exceeds the vapor pressure of the atmosphere. After that, evaporation increases as temperature and vapor pressure increase. It finally levels off in a temperature as its vapor pressure equals the vapor pressure of the atmosphere. Then the temperature remains constant no matter how high the flame. The evaporation, or boiling, that is taking place is keeping the temperature constant throughout the evaporative cooling process. Laws of food thermal moisturization. When foods are supplied with heat from vapor-laden hot air only, their steady state temperature will become greater than that of the air wet bulb temperature and less than the air dry bulb temperature. When foods are supplied with heat from vapor-laden hot air only, the evaporation rate of food moisture is dependent upon the difference between the dry bulb temperature and the surface temperature of foods. The importance of this first law is key. When considering the matter of food safety, it is controllable wet bulb temperature that assures the temperatures specified by health codes will be met. Hot food holding equipment with only dry bulb temperature control cannot assure safe temperatures because the food temperatures are always less than the air temperature setting. This is seen in hot holding cabinets that only use sensible heat in the chamber. Conventional ovens have only dry bulb temperature control and give little control over food temperature when cooking. It requires constant attention to assure food safety. As frequently the case with the development of new technologies, new terms or words are needed. The scientific world uses thermalizing to represent the heat transfer phenomena in each of the processes. In this text, the term thermal moisturization is coined to represent simultaneous thermalization and moisturization of foods. C-Vap establishes the importance of utilizing two different heat sources to cause it to be a dry convection oven at one end of the scale and a steamer at the other end. It is degrees of wet and dry that is greater importance to the end user. And now we toss it over to Chef Sam Brown at Winston to discuss the thermal moisturization chart, which helps explain this phenomenon.
Hi everyone, my name is Samantha Brown. I am the corporate research chef here at Winston Industries, and I am going to explain the concept or the magic of C-Vap using the chart behind me that no one can pronounce. So this is the food thermoisturization chart. Thermoisturization. Everybody say it with me. Thermoisturization. This is the world of C-Vap and cooking in general, really. Here we have, if we look at these pretty colors here, we've got on the chart proofing, moist holding, steaming, moist cooking, firm hold, crisp cooking, baking. We've got our temperature danger zone here. But really the key to all of this is understanding the X and the Y axis. I feel like when I explain to people and customers how to create a program, not knowing what the first step is, come to this chart. It will get you on the diamond, not just in the ballpark, but in the diamond. You may need to tweak it a little bit for whatever your product is, but it'll be much closer than shooting in the dark, so to speak. So let's start at the bottom. The x-axis is your vapor temperature. Okay, don't look at the names. That is your vapor temperature. With your new C-Vap, this is the vernacular that's used, and that's what I want you to remember. Vapor temp is this range of numbers on the bottom. Now the y-axis, which is this puppy, the vertical one here, is the differential temp. Sam, what does that mean? That means that you're using two forms of heat. You're using dry heat, which is your air heat, and you're using moist heat, which is your vapor heat. The difference between the two numbers is the differential. Okay, let me give you an example. Say we're doing fried chicken and we want to hold it, which is basically what C-Vap was invented for. It was holding fried chicken for KFC. So I'm going to go over here and I'm going to think, okay, I want moist hold, I want crisp hold. So I'm going to look at the center of this circle. Let's just go right in the center and go down to the vapor temp. Standard vapor temp for a crisp hold for fried chicken, really anything that's crispy, it's going to be 160. And then if I go over here to the y-axis, it says 80. That's not 80 degrees Fahrenheit, that's 80 degrees on top of the 160. 160, 240. 160 vapor, 240 air. And you can use this method for any end product or any whatever your target goal is. That's when you don't have a program, come to the chart and try to figure it out. And if you can't do that, come talk to me or Barry or anyone from the sales team or customer care. I'm gonna get you straight. All right. Hope that helps, and we'll talk to you soon. Bye.
Thanks, Chef Sam. Hopefully that helped everybody. I haven't lost you, have I? All right, well, we're getting back into the science. Thermalizing food, a wet body science. The laws of thermoisterization provide understanding of the control of the food quality utilizing two heat sources. The laws state how food temperature and food moisture can be controlled through control of wet bulb and dry bulb temperatures of the food atmosphere. The basic reason for importance of wet bulb temperature control is as follows. 1. The large vary amount of moisture in all fresh foods. 2. The enormous heat and vapor of the water. 3. The ability to accurately control the amount of water vapor in a food's atmosphere. Temperature control and hot food holding, otherwise known as wet bulb control. If the food has a naturally wet surface, think pastas, vegetables, sliced or cut meats, peeled potatoes. The evaporator temperature has far greater influence on food temperature than does the air temperature. This is because the evaporator maintains vapor in the food's atmosphere, and that characterizes its temperature. The food's moisture has a vapor pressure. Since two wet bodies share the same atmosphere, they must acquire the same vapor pressure to become the same temperature. Think about that boiling water example we gave a minute ago. Since the temperature of the evaporator is precisely controlled, the food temperature is precisely controlled also. The thing that anchors food temperature so tightly to the temperature is the balance between condensation and evaporation. That is, its equilibrium. If the food cools to a temperature below the evaporator temperature, moisture will travel from the evaporator to the food to heat it. If the food is at a higher temperature than the evaporator temperature, moisture will evaporate from the food to cool it. Since evaporation and condensation are very effective heat transfer phenomenon, the food is boxed between two highly effective heat transfer phenomenon, and it must acquire vapor temperature. Foods behave like wetted gauze on a thermometer bulb. If their mass is large, it may take hours to acquire the steady state temperature dictated by the evaporator of the hot food holding cabinet, but they will inevitably do so. It makes no difference whether the foods are placed in the atmosphere at a higher temperature or a lower temperature than the evaporator temperature, nor their size. They will finally stabilize at the temperature measured by a simple wetted thermometer bulb. It is the heat transfer into or out of the food due to the condensation and evaporation that overwhelms the heat transferred by the dry air. This causes food temperatures to be more approximately evaporator temperature than air temperature, but always greater than the evaporator temperature. It is this fact that makes it useful in controlling the minimum food temperature, thus critical to food safety. It should be noted that immersion circulators utilized for sous vide cooking uses wet bulb temperature to heat food that has been vacuum sealed. Setting immersion circulators at 140 degrees, the bagged food will eventually reach 140 degrees. C-Vap uses that same principle to control food temperature with the wet bulb or heated evaporator in C-Vap equipment to reach a precise temperature. It's dialing in those two settings that help you obtain the precise temperature that is desired. Now that we've discussed the wet bulb side of things, let's talk about the dry bulb side of things, or crisping of foods in a hot food holding setup. As the air temperature is elevated over the evaporator temperature, it then raises the food temperature slightly over the evaporator temperature. This causes a small net evaporation of food moisture, but controlled. Some of our experimentation has shown that one must elevate the air temperature over the evaporator temperature by 6 degrees to get 1 degree of elevation of food temperature over the evaporator temperature. For small to intermediate values of differential, 0 to say 40 Fahrenheit, the food temperature increases over the evaporator temperature 1 for each 6 Fahrenheit of differential. In the 40 to 80 Fahrenheit range of differential, the evaporation rate begins to exceed the rate that the moisture can be fed from the interior of the food. The effect is that evaporative cooling is diminished as the food temperature approaches the air temperature. One should understand that food is primarily water, that the temperature of water bodies is most effectively controlled through the forces that control condensation and evaporation. That a wet bulb measurement relative to the temperature of the water is an indication of evaporation or condensation, and that by controlling wet bulb temperature, one can control the temperature of the water. Air temperature, dry bulb temperature, controls evaporation, thus texture or browning of the foods. Relative humidity does not control anything. It is the components of relative humidity that control the two components of thermalized food quality. One can set food temperature at 150 degrees and obtain 150 degree food whether one is cooking, holding, or merchandising foods. Controlled vapor cooking. The factors that one must control to thermalize cooked foods are identical to the ones that prevent change. Use of science, however, does not offer new ways to cook. More correct and better control of the cooking processes is what is offered. As cold foods are placed in a traditional oven, they begin to rise in temperature. As they rise in temperature, evaporation begins and increases to a very high rate as the temperature increases. Evaporation slows as the interior food moisture can no longer be supplied at the rate it can be evaporated. The food has become dry. Evaporation is counterproductive in several ways. It slows the heating process through evaporative cooling. It also wastes energy and it removes food moisture important to palatability. Prior to the foods being done, they're underdone. Afterwards, overdone. It is necessary that the end user monitor the process closely to remove foods when the doneness temperature is reached. Utilizing evaporator and air heat sources as described previously, one can thermalize or cook foods. As uncooked foods are entered into the oven cavity, foods are heated by both heating systems. Until the foods reach the temperature of the evaporator, there can be no evaporation of moisture of the food. Without evaporative cooling, they are heated more rapidly than in traditional ovens. As foods reach the selected doneness temperature, they discontinue their temperature rise. If foods are not removed from those ovens, they then remain there for extended periods of time and at the selected doneness temperature with moisture adequate to assure succulence. Through the technical correctness of this method, much of the attention to produce quality food is eliminated. If foods are to be textured or brown, dry bulb heat is applied that will evaporate only what is necessary to obtain the surface aesthetic desired. While we've delved into the technology and science behind controlled vapor technology, one should now understand that air heat only cooking systems cannot cook to precise doneness temperature on a consistent basis. Dry air heat only systems have very little tolerance for errors in cooking time and result in product shrinkage or overcooking. Dual air heat and water vapor control both final food temperature and food moisture. Dual air heat cooking systems are highly tolerant of variations in cooking time. Thanks for sitting in on the science of controlled vapor technology compared to combi ovens, convection ovens, and sous vide cooking. Let's toss it over to Chef Sam in the Winston kitchen to give us some fun demos on controlled vapor technology.
Hello and welcome to the Winston Kitchen today. My name is Samantha Brown and I'm the corporate research chef here. So today we're going to look at controlled vapor technology and as it pertains to cooking and holding. And we're going to run a whole gamut of items. So we're going to look at an overnight roast using a top round. We're going to stage some steaks and then reverse sear them. We're also going to look at hot holding from soft to crisp things, and of course we're going to make creme brulee without a water bath. Our first demonstration, we're going to show how we can do an overnight roast with an inside top round, beef inside top round. So what I did is I got the full top round, I trimmed it down, I prepped it with some dark soy, some Montreal seasoning, and then I put it on a rack. You'll see in a second. I put it on a rack in a hotel pan. I calculated, or I weighed up the roast, and our raw weight was, I don't know if you can see this, but it was 12.28 pounds on the raw side. So I'm gonna pull it out. And I have actually already weighed it earlier. The cooked weight was 10.09 pounds, and our cook yield is 82%. I would say that for this particular meat at this program, and our program is 130 on the vapor, 180 on the air, and that was set for, I believe, 5.5 hours. We did a cook, and then it went into an overnight hold for an infinite amount of time at 130 on the vapor, 132 on the air. So 82% yield for this meat, which is very lean, is, I would say anywhere between 80 and 90 is great. Are you going to see that through convection? Probably not. Are you going to see that in other forms of preparation? probably not. You're going to see in the 70s for this particular meat, I would guess. Using C-Vap gives you an advantage because when you set the vapor temperature, you are setting the temperature for the inside of the food. It is almost a safeguard, if you will. That temperature of the internal temperature of your roast or whatever you're cooking should not exceed that. So you can have perfectly medium rare roast, medium, whatever. So like this one is I set for 130. That means the internal temperature should have never gone past 130. So if you would like it more done, you would 135, 140, whatever that is. So I'm going to slice down the center. And you're going to see the consistency from end to end. There's not going to be a well done end point. There's going to be a nice rosy pink color from end to end, top to bottom. So there is no bullseye. There is no. You're not going to see a center red ring. You're not going to see graying towards the outside. There really is no rest period using this type of technology. You can pull it out as you need it and slice it and go. So for the asparagus, we did a sous vide, or actually we did a steam style. Actually, we did both. We did 200 in a CHV, so 200 vapor, 200 air. We did bag version and then just out to the element, so to speak, for about 12 minutes. And the cool thing about that, I feel, is the ease of execution, consistency. You can use a bag, it's not necessary, but if you do use a bag, especially for a product like asparagus, which is going to go through some enzymatic breakdown, you stop that process. And not only do you stop that process, but you've also extended the life of sous vide. So extended the shelf life by having it in the bag. You've created a sterile environment, if you will. You're not touching it. You can cool it down in ice water. You can put it in the refrigerator. No hands have touched it. So there's pros and cons to both of those applications. Let's talk a little bit about what sous vide is. The literal translation is French for under vacuum. Of course, we all know that. But it's also, we'll go a little bit further into it. It's a technique of cooking where you're technically cooking under vacuum, but at a very low, precise temperature. And depending on what you're cooking, it could be for an extended period of time, like for, there's a beef rib recipe out there. It's 48, 72 hours, whatever it is. But when you think of that, the product itself has got a lot of connective tissue, and the reason you're doing that is because if you cook protein too fast, the fibers tense up and you lose all your moisture. So at lower temperatures, precise temperatures under vacuum, you can extend the lower temperature precisely for extended periods of time. So you can cook, you can bring that protein up slowly, and you're not worried about tensing the fibers, the protein fibers, and squeezing out any of the water. You also maintain a color. You maintain that color, so the hemoglobin at a certain point will completely gray out. So that's another advantage of using sous vide or sous vide type processing. So we have some strip steaks that we have been holding, or actually C-Vap staging. We have been staging in a Winston cabinet for a couple hours now at 1:30 and 1:30. And what we're going to do is just pat the outside of it dry We want a nice sear. So this is considered what reverse searing means. So you basically cook the protein first and then high temp sear to finish, whether it's grilling or we're going to pan sear. You could broil it, you stick it in the deep fat fryer. So I'm going to season both sides with a little coarse kosher salt. And when my pan comes up to temperature, we'll sear it. So now we're going to sear the stage steaks in a little duck fat. And I've sprinkled both sides with some kosher salt after I've dabbed both sides of the steak with a little bit of, to remove the moisture for both sides. I'm trying to get the steak as dry as I can so I can get a better sear on it. So think of speed to service. You can do staged chicken breast, staged pork chops, staged steaks like we're doing. You can do strip steaks, fillets, ribeyes, any cut of meat. And what's happening is that we've already brought the internal temperature of the steak up slowly. And we're finishing it quickly, high heat method, just to give it color, to give it some of that nice mayo browning, the caramelization that happens when you sear. So for a restaurant, this means faster ticket time, more consistent product. There's an educational piece that goes with it, but there's a learning curve, depends on what your staff already knows. This could be an easy implementation to what your current programs are. So try and get that fat cap on the outside of the steak nice and crispy. A little on the other side, and then we'll be done. So a 1-inch, 12 to 14 ounce strip steak, perfectly medium rare, end to end, and under 3 minutes. So, I'm gonna do one more. So let's slice it open. Ooh. Creme brulee is a mixture of egg yolks, heavy cream, sugar, vanilla. It's very simple. and it's very easy to screw up. I was a pastry chef for a very long time, and I would overcook them. I wouldn't have the temperature right. My water bath would run out of water. There are just a myriad of issues that I have found in dealing with creme brulee and making creme brulee. So that being said, with certain technologies, you can actually cook creme brulee without a water bath, and it comes out almost perfect every time. There are certain technologies out there that you can utilize that you don't really need a water bath. So for items like cheesecake or flourless chocolate torte or creme brulee, for instance, you wouldn't need to deal with that hassle. It's not safe. You're pulling hot items out of that cabin. It's heavy, it's hot, and then you also have to think about the quality. If you're going to slosh it, it's going to ruin your beautiful creme brulees or whatever you're doing. So it's just better to cook without the water bath. So we have some coming out. And this has been in a 100% humidified oven. And what I mean by that is the dry bulb and the wet bulb are equal to each other. And I believe it is at a temperature of 200. So what happened is you've already cushioned the air around the creme brulee with moisture, and you're still heating it delicately like a water bath would, without the need for a water bath. So here we have some very hot, very set custards. Here, these need to be refrigerated. I would say at minimum 4 hours, but overnight is best. And then for the next day, or maybe if you're preparing these in the AM for use in the PM, you would refrigerate those for, like I said, a minimum of 4 hours. Get them out, sprinkle some sugar on the top, and then go about your business about bruleeing the top. So the goal is to get a nice, even candy coating on the top. And then, of course, by the time it makes it to the customer, it's already set and glazed and glassed. So we've seen controlled vapor as it pertains to cooking. A specific product that I think is definitely beneficial for this type of technology is eggs. Not only can you cook in it, but you can also hot hold for an extended period of time. So here in the bottom, we've got some scrambled eggs that we cooked in a CHV. Holding eggs, honestly, working in the restaurant business, I never would do that unless it was poached or maybe soft boiled or something like that on the stove. With controlled vapor, you can actually, that gives you a lot of bandwidth in the kitchen. You can hold over easy, poached, scrambled, whatever variety of egg, and for an extended period of time, and keep your quality. So here we've done some scrambled eggs. It's been holding for quite a while. I would say upward towards 3 hours. Now, would you do that in the back of the house? Probably not. I would say an hour to 2 max, but you can tell how fluffy. They're still bright and brilliant, and they're not rubbery at all. They haven't turned to green, so that is a huge benefit for eggs. Now here in the top, you'll see again the benefit of controlled vapor. These are sunny side up eggs that have been holding for well over 3 hours. And I'm going to cut into one of the yolks. So sunny side up eggs in controlled vapor, 3 hours. We're getting a film on the top. Would you ever go that long? Probably not. But The yolk is still running. So controlled vapor it's a good segue to the spectrum of texture. So you can go from things that are soft and delicate like eggs to something that is a little more hardy and robust like tortilla chips or fried chicken. So these items, let's see, of course the program is going to be different depending on what your target goal outside texture is going to be. Of course, these have been holding for quite a while as well. They've been holding for about 3 hours at 90, 180. The internal temperature of this pan is about 175 to 178. Nice and hot, nice and crisp. You can not a stale chip in the bottom.
Thanks a lot, Chef Sam. That food looks amazing. And thank you for your time today. We really appreciate it. If you have any questions, reach out to FS Marketing at Winston IND or email our customer care department at customercare@winstonind.com. Don't forget to fill out your questionnaire and submit it to FCSI for your CEU credit. Thanks again for joining us today. Follow us on social media and stay safe.